Next, we want to look at the average value of a continuous function. So suppose we have some function that tells us the temperature recorded at a weather station on a certain day. So then in this graph, the t-axis or the horizontal axis will just be the hours in the day, and we're using an Army time 24-hour period. And this axis gives the temperature at those particular hours. So let's say we want to find the average temperature for this day. Now, usually to find an average, what do? We just take all the values, add them up, and then divide it by the number of values. So we can express this using summation notation. So using summation notation, let's just suppose we have n items that we're adding up. So this notation right here is just saying add up all those n items, and then we divide it by n. So this is how we can express an average. And this Ti right here just represents the various values of the temperature. So say we wanted to look at 6 values of the temperature, then we'd have T1 could maybe be like this value when time equals 4. T2 could be this value when time equals 8, and so forth. So we just pretend we have 6 values we want to look at. So then we have a T1, T2, T3, T4, T5, T6, add them all up, and then divide them by 6. In this case, n would be 6 because we have 6 items we're looking at. So let's just suppose that we wanted to find the average temperature, and we chose 6 times throughout the day, picked those temperatures, and found the average of those 6 temperatures. So just pretend we have these ones that I've marked out here on the graph. So say we use those 6 values, find the average. Well, if you look at this point right here, on to the left of that section of the graph, we use this time period, this reading, and to the right of that time period, we use this reading. Both of those readings show a higher temperature than this section that I've circled. So the section that I've circled isn't really contributing to the average. So the average may not be very good, be very representative of the actual temperature on that day, because the values I picked didn't really account for this little dip in the temperature right here. So we kind of want to do a more accurate average than just picking 6 random values. So you can think, well, what if I pick maybe 12 values, or 18 values, or 24 values? It seems like the more values I pick, the more accurate my average will be. So that's correct, and the more values we pick, the more accurate the average will be. So what we can do is just let the number of values we pick go to infinity. So basically what we want to do is take the limit as n goes to infinity of this average expression. So this will be our definition of the average value of the temperature, or in this case we're doing temperature, but it could be any function, over the domain. Now if you look at this expression, it's pretty close to our definition for an integral. Now this is our basic definition of an integral, but because we're talking about temperature T and then time lowercase t, we can rewrite this to be capital Ti and delta t lowercase t instead of delta x. But for this scenario, this will be our definition of an integral. And you can see it's pretty close to what we have here. It's just our average function has this 1 over n, which we don't really see in our integral definition. And then our integral definition has this delta t, which we don't really see in our average. So remember what delta t is equal to. It's just the length of the interval, so b minus a if the endpoints of the interval are a and b, divided by n. So for our particular example, b would equal 24 and a would equal 0. So then we get delta t is equal to 24 over n, which you could also write as 24 times 1 over n. So now looking at our average, we see that we have that 1 over n. So if we could just multiply that by 24, we would get our delta t. And then our average would be exactly equal to the limit. Our average would be exactly equal to our integral definition. But of course I can't just pop a 24 in right there. So what we can do is multiply by 24 over 24. And now I can rewrite this as 1 over 24 times 24 over n. And I know 24 over n is equal to delta t. And then the 1 over 24, it does not depend on n, so let's just move it outside of the limit. And now I have this part right here exactly matching the definition of an integral. And if I want to, I could put this delta t right here, just so it looks exactly like this, if you want to, but it doesn't really matter. So now that this looks exactly like the definition of an integral, we can replace it with the integral from the endpoints of our interval, which is 0 to 24, of our function f of t with respect to t. So now we know how we can find an accurate average. We can use the integral to accomplish this. And remember what this 1 over 24 came from. That's from the endpoints of the interval. So it's basically 1 over b minus a if b is the endpoint of your interval and a is the starting point. In this case, b is equal to 24 and a was equal to 0, so it just equaled 1 over 24. So this discussion leads us to this definition of the average of a continuous function. So it's basically what we just talked about. It's 1 over b minus a times the integral from a to b of the function. Now, we can look at this a slightly different way. If we multiply both sides by b minus a, then we'll get this equation. And so basically what it's saying is that if we make a rectangle with width b minus a and length or height y, which is the function value, the average function value, then we're going to get this rectangle. And when we multiply b minus a times y, we'll get the area of this rectangle. So what this equation is saying is the area of that rectangle is exactly equal to the area underneath the curve of this function. So if we find the average value of a function and multiply it by the width of the interval, it will be exactly equal to the total area underneath that function. Now, an important thing to note is that the units for the average value will be the same as the units of the given function. So like if you have speed, the function you have is measuring speed over velocity, then if you find the average, you're finding the average speed. So the units would still be miles per hour or whatever the speed units are that you have. So basically, if you're given a function that's measuring a rate, when you find the average value, you're still, the units you have are still a rate. It's just the average rate. So that's why the units will be the same. So the average value is not telling us the area underneath the curve. If it was telling us the area underneath the curve, it would be different units. It would be the accumulation. So if it was like a velocity function, then the area underneath the curve is distance. But we're not finding that. We're finding the average value. So that's why the units are the same. But if we multiply the average value by the width of the interval, then we would find the area. But this equation up here is just for the average value, and the average value, again, is the same units as the function we're finding the average value of. So let's do an example. Let's find the average value of the function x squared over the interval 0 to 2. So like we just talked about, the average value is given by this equation right here. So in this case, a is equal to 0 and b is equal to 2. So we can just plug everything into our formula. You can see I plugged in the values of b, the values of a, and then the value of f of x, which is x squared. Okay, so now we can just evaluate the integral. So first of all, this guy is just equal to 1/2. Now let's find the antiderivative of this, which is 1/3 x cubed. Now we can plug in the limits of integration. And also, you can just factor this 1/3 out if you want to. Sometimes it makes it a little bit simpler to evaluate. So let's go ahead and do that for this problem. So that means we can write it like this instead. And then when you multiply the 1/2 and 1/3 together, you get 1/6. So we get 1/6 times x cubed, and then the limits of integration are still from 0 to 2. Okay, so now let's plug in the limits of integration. So we get 1/6 times 2 plugged into the antiderivative. So we get 2 cubed, and then minus 0 plugged in to the antiderivative. So we get 0 cubed. So then we'll just get 1/6 times 8, which equals 4/3. So 4/3 is our average value.